subject is entropy. Entropy is a state function. Remember, a state function means that you can come to the same conclusion in a number of different ways, which means you can calculate entropy a number of different ways and you will come up with the same answer. Entropy is a measure of the randomness or disorder of a system. It's a measure of the probability of the number of arrangements available to a system. The greater the possible number of arrangements, the greater the entropy. Okay, let's think about that. If you have something that is highly organized, that means it's everything has a place and everything in its place. It does not have a lot of arrangements possible. If your room is completely clean, all your clothes are hung up on hangers, each hanger is labeled as to the article of clothing that belongs on it, that means that it is not very randomized. Each piece of clothing has one arrangement, the hanger that is assigned to it. Nobody in real life lives like that. I'm certain that most people just throw their clothes in the closet. That means that there are plenty of places for the clothes to be anywhere they land into the closet. Such a system would have a high degree of entropy because there are lots of places for the clothes to fall. Therefore, it's very disorganized. All right, let's talk about entropy. The change in entropy for a system, and remember we're talking about chemistry, so when we talk about chemistry we're going to be talking about a chemical reaction. So if you have the reactants combining to form products, the change in enthalpy for this system can be calculated by finding the change in enthalpy of the final product minus the change in enthalpy of the initial, the reactants. If the enthalpy of a system is positive, that's an increase in entropy. That generally that means the process is spontaneous, is thermodynamically favored, and will happen with outside intervention. As a general rule, if the entropy of a system is negative, that is a decrease in entropy, the process is generally non-spontaneous. You can make a statement that says that the universe is lazy. It likes a tendency towards disorder, does not want to hang up its clothes. Okay, you can look at certain chemical equations and by inspection see if the entropy of that reaction will increase. If in a chemical reaction you see that the products have gone from a solid, very organized state to a gaseous random state, that would denote an increase in entropy. The entropy of a solid is less because it's more organized than the entropy of a liquid, and then a liquid is more organized than a gas. If the temperature increases, the entropy of the system also increases. That makes sense because temperature is equated to kinetic energy. So if you have particles that are moving faster, they have the possibility to be in many places, therefore they have a greater entropy. When a solid dissolves, the entropy increases. A solid is highly organized. The particles are fixed in one spot, vibrating along in that spot, whereas an aqueous solution has a particle surrounded by a solvent, and there are more places for those particles to slide by in the liquid state. When the number of particles increase from the reactants to the products, then the entropy increases as well. Count the number of moles, or look at the coefficients. On the reactant side, we have 2 moles of particles of SO3. On the reactant side, we have 2 of SO2, 1 of O2 for a total of 3 moles of gas. So the reactants have less entropy than the products, so delta S in this case would be positive. When molecular complexity increases, then so does the entropy. In KCl, there is just the electrons from potassium completing the octet for chlorine, and it's just in this type of arrangements. When you have calcium sharing its 2 valence electrons with 2 chlorines, then there are different ways for these to combine. There are more possible arrangements. The more atoms in a compound, the more entropy for the same reason as above. Okay, let's look at a few examples. In exercise 2, solid sugar is added to form water to form a solution. Remember, a solid is, by your junior high definition, a highly organized fixed particle vibrating in one place. You add it to water, it forms that nice little solvation complex where the solvent surrounds the solute, and then this solvation complex is free to move in the solvent particles. Iodine vapor, that would be gas, condenses on a surface to form iodine crystals that goes from the highly randomized gaseous state to the solid state, so the entropy decreases. Which of the following has the largest increase in entropy? A solid going to a gas, that is certainly positive. We have 2 moles of gas on the side, in example B, in the reactant side, and 2 moles of gas on the product side. That's a push. There really is no measurable change in entropy, at least not qualitatively. And here we have potassium nitrate evaporating out to form the crystal. So that is a negative situation. Delta S decreases. Here we have the very organized network solid, a diamond, going into graphite. Graphite is less organized and than the diamond, so that is a positive change. Which one is most disorganized from A to D? When we're comparing which one of these positive entropies is more disorganized, and that would definitely be scenario A. You can calculate entropy from tables of standard value. You can save yourself a lot of heartbreak if you remember now that those tables are measured in joules per mole per degree Kelvin. Everything else is measured in kilojoules. What's everything else? Well, the delta H, and something you'll learn about soon, delta G. So when you look at this, please recall these are in joules. This is a state function, so you can find the change in entropy for the reaction is equal to the sum of the change of enthalpy of the products minus the sum of the change of enthalpy of the reactants. We are given this data, and this is per 1 mole. You will notice in some of our species in this reaction we have 2 moles, so we have to take account for that. So I see that I have 2 moles of SO3 whose value is 248.1, and then I must subtract the enthalpy values for the reactants. 2 times the value for SO2, which is, oops, I messed up. This is 256.6, and this is 248.1 times 2 minus the O2 value, which is 205.3. And when I do my math, I come up with the answer minus 188.3. Everything has an entropy value. So there are no negative values for entropy. The lowest entropy value is 0. The entropy value for a perfect crystal at absolute 0 is 0. That does not happen on Earth, so please recall that there is no 0 value for entropy and there are no negative values for entropy.